become 3s square 18s plus 18. अब इसके रूट्स फाइंड आउट करना, दो रूट्स आएंगे, दोनों में एक वैलिड ब्रेकअवे पॉइंट. दिस इज द प्रोसीजर. रूट्स फाइंड आउट करो क्या है. On-off controller. It is a natural extension of on-off controller. ये on-off controller नहीं है, ये on-off controller का extension है. हाँ. बाद में गलती से proportional controller is on-off controller ऐसा कुछ ऑप्शन आया तो on-off controller को पिक करके आगे मेरा कलर नहीं पसंद. क्या है? ये extension of on-off controller. ये on-off controller नहीं है. Second. Similarly, on-off controller भी proportional controller नहीं है. एग्जाम में यह भी पूछता, on-off controller is proportional controller, non-linear controller, ऐसा ऑप्शन है. It is not proportional controller, it is a non-linear controller. दो ही स्टेट्स है, on and off. और इसमें दो स्टेट्स नहीं है. It is smoothly opening and closing the trap. Second point, the band of errors where every value of error, the band of errors where every value of error has a unique value of controller output, has a unique value of controller output, is known as proportional band. Is known as proportional band. Next, the disadvantage of this controller is it exhibits a permanent residual error known as offset. It exhibits a permanent residual error known as offset at its operating point. Now listen here. When you reduce the width of the proportional band, what is proportional band? It is a band of errors where every value of error has a unique value of controller output. As the width of the proportional band reduces, यहाँ पे जो error की quantities है, they will not change. They will remain. Every value of error has a unique value of controller output. So when you change the width of the proportional band, these quantities will not change. For the same values, the controller output will change. For the same values, the controller output will change. You understand? So because this is defined as the band of errors, that every value of error has a unique value of controller output. When you reduce the width of the proportional band, this error quantities will remain same. For the same values, controller output will change, whether you increase it or reduce it. Is this clear? Question number 20 देखो, chapter 3, page number 63. maximum value of controller output is 100 volts and is obtained when the input error is 1 volt. So the equation is P is KPE. 100 volts you are getting for 1 volt error. Kp value is 100. What is proportional band? 100 by Kp. 100 by 100 is 1. Percentage proportional band will become 1 into 100 equal to 100%. अगर 100% proportional band है, for 1 volt error you are getting an output of 100 volts. For 100% proportional band, for 1 volt error you are getting an output of 100 volts. By changing the width of the proportional band, यहाँ पे एरर की जो क्वांटिटीज है उसमें कोई चेंज नहीं होगा. इसमें चेंज होगा सिर्फ कंट्रोलर आउटपुट में चेंज. अगर ये प्रोपोर्शनल बैंड का विड्थ अगर हम 20% अगर हम कर दिए, व्हाट विल बी द आउटपुट? 20 by 100 into 100 is 20 volts. For the same 1 volt error, the output will be 20 volts. ये इसका आंसर है. So by changing, increasing or reducing the width of the proportional band, only the controller output will change, not the input quantities. क्योंकि एरर तो आ गया यहाँ पे, 1 वोल्ट एरर है. अब जो कंट्रोलर आउटपुट है, ये प्रोपोर्शनल बैंड चेंज करने से ये तो चेंज नहीं होगा. क्या चेंज होगा? आउटपुट ही चेंज होगा. You understand?
Consumption number answer 1 volt 20 volt D.
Finished? Now listen. The second type of control mode or controller mode. The second type of controller mode we call it as integral controller, or it is called as integral mode. In an integral mode, the rate of change of controller output is proportional to error. Is Ki into E. This Ki, we call it as integral scaling. The actual controller output is obtained by integrating this equation. That is why we call this as integral controller. P of S is equal to Ki by S into E of S. So the transfer function of an integral controller is of the form of Ki by S, with E of S as input and P of S as output. We are defining reset time as Pi is equal to 1 by Ki. ये reset time क्या है, इसका क्या significance है, appropriate time पे बताऊंगा. अभी सिर्फ लिखो 1 by Ti integral of E dt. We can also write the transfer function of integral controller in terms of this reset time as 1 by TIS, with E of S as input, E of S as output. So either this or this is a transfer function representation of an integral controller. Now let us see how this fellow is going to work in this plant. This is error, this is the controller output. So at some point of time t equal to t1, a sudden error of magnitude A has occurred in the system. What is the meaning of the sudden error? We already know. We are using an integral controller here. What is the transfer function of an integral controller? 1 by TIS. Let us see how this fellow is going to work. The controller output is 1 by Ti integral of A dt, because E is A. It is A by Ti into T. This is the response of the controller. This is how he is responding. A by Ti into T. At this point of time t equal to t1, maximum error the system mein ho gaya. Suddenly the inlet has changed. Large quantity of water came and fell into that. Suddenly, the pani ka level suddenly jumped to a new value. Now, itna sudden error to hai system. Water level is somewhere here now. Error to abhi maximum hai system mein. The controller ka output kya hai? 0. He is not responding. Water level is somewhere at a new value. But what is the controller output? 0. Previous fellow, he immediately responded. But this fellow, error तो हो गया वहां पे. इसका response क्या है? 0. He is responding. He is sending a control signal. But this control signal that he is sending is very slow. This is the disadvantage of an integral controller. His response to errors is very slow. अब मेरे को ये चेक करना है whether this response is fast or slow. I want to check mathematically. To check mathematically, we know that for any system, when you subject that system to sinusoidal input, output also will be sinusoidal. But the output will have different magnitude and different phase. Suppose if the output is exhibiting phase lead characteristics, इसका मतलब क्या? Fast response. If the output is exhibiting phase lag characteristics, what does it mean? So if I want to check whether this response is fast or slow, you must perform sinusoidal analysis of this controller. Subject this controller to sinusoidal input and see whether this controller will give a phase lead output or phase lag output. Because input is error, we assume that error to be sinusoidal, and this is only mathematical analysis. Don't ask me to show sinusoidal error here. I can't show. So I am just doing sinusoid analysis to check whether this response is fast or slow. So let E equal to sin omega t. It is 1 by Ti integral of sin omega t dt. This is 1 by omega Ti minus cos omega t. It is 1 by omega Ti sin of omega t minus pi by 2. So you see, for sin omega t input, phase of the controller output is leading or lagging? How much angle it is lagging? pi by 2 phase lag का मतलब क्या है? बहुत fast response है या slow response? ये disadvantage ये controller. So no doubt he is responding. Suddenly inlet change होने से water level सब में इधर चलेंगे. Error तो हो गया यहाँ पे. He is responding, but his response is very slow. Though he is slowly responding, whether he is removing this error or not, we have to check. Which means whether he is bringing the water level back to set point value or not, we have to check. So let us check that. That means this error is this error becoming completely zero or not, we have to check. How to check that? You have to evaluate. This should become zero. Let us evaluate that. limit s tends to 0, s a by s, r by rcs plus 1 by 1 plus r by tis into 1 plus ts. This ss gets cancelled. Magnitude of ess will become ar by 1 plus infinity. How much? He is bringing the water level back to set point 12. But what is the use if he is doing it very slow? You understand?
ग्रुप सेंसिटिविटी तो कल पढ़ा है, इसलिए हमें सुबह चेक करके बैठे हैं लिखने, कहीं हम गलती से लिख चले गए बीच में।
Disadvantage of integral controller is the disadvantage of integral controller. The disadvantage of integral controller is its response to errors is slow. However, it is capable of eliminating the steady state error. Capable of eliminating the steady state errors completely in the system. We have the last pure mode as derivative mode. So derivative controller is also called as derivative or rate. Derivative controller is also called as rate controller. It is called as rate controller because the controller output is proportional to rate of change of error. It is kd into dE by dt. This will become kd s into E of s. This is kds. E of s is the input. E of s is the output. This kd we call it as rate constant. We are defining rate time. What is the significance of this? I will tell you at the appropriate time. PD is equal to KD. We can also express the transfer function of a derivative controller in terms of the speed. This is TDS. E of S is the input. P of S is the output. Now let us see how this fellow is going to work in this plant. Say at some point of time a sudden error of magnitude A has occurred in the system. How is the controller responding to the sudden error? We will see. This is Td d by dt of A, since E is equal to A. What is derivative of constant? 0. Sudden error means suddenly if inlet changes, water level suddenly jumps to a new value. If sudden errors occur, what is the output of the derivative controller? 0, which means he is not responding. Is this an advantage or a disadvantage? This is the disadvantage of a derivative controller. It cannot respond to sudden errors. If it is unable to respond to sudden errors, then let us see how this fellow is responding to AT. What is the meaning of AT? Agar yes, large quantity of water suddenly comes and falls into the tank, वो sudden error. Suppose continuously water is falling into the tank at some rate, at some fixed rate. जैसा अगर टैप को हमने 10% ओपन करके छोड़ दिया, what will happen? Water will be falling continuously into the tank, into the bucket. What happens to water level? Gradually it also starts rising. Like that, when this is changing at some rate, constant rate, water level also will be rising constantly at some rate, it will be rising. Error also is changing constantly. Yes or no? This is called as AT error, represented as AT. If this is the error, let us see how this fellow is responding to this error. It is Td d by dt of AT. It is ATD is the response. This is how he is responding. ATD is the response. If you observe, at t equal to t1, what is the error? Huh? But what is the controller output? Maximum. To which setting is sending a signal. Error is still 0. Error is still 0 means this is just about to change. It has not even started changing. Error, water level is at the set point value only. Error is 0. Water level is about to rise. Error is about to occur. Error has not even started occurring. Before the error has occurred, this controller is sending a signal to the control element. Before this is rising, it is about to change, it has not even started changing. Suddenly this fellow is opening the tank. What will happen? अभी पानी का लेवल सेट पॉइंट पे ही है, एरर 0 है, but controller is sending a sudden signal to the control element. Suddenly he is opening the tap. To which setting he is opening? What happens to the water level? It will fall. अब एरर होने से पहले ही sending a signal. So fast भी नहीं, unusually fast. अब एरर हुआ ही नहीं, ये होने वाला है, एरर होने से पहले अगर कंट्रोल सिग्नल अगर हम दे रहे हैं, व्हाट इज हैपनिंग? वाटर लेवल विल फॉल. तो क्या होगा? आउटलेट विल बिकम मोर देन इनलेट होगा. अगर आउटलेट मोर देन इनलेट हो गया तो क्या होगा? खाली हो जाएगा. टैंक विल बिकम. व्हाट इज दिस फेलो डूइंग? By sending a signal before error, is emptying the tank. पानी का लेवल तो सेट पॉइंट पर रखना छोड़ो, दूर की बात. Is emptying the tank. क्या ये एडवांटेज है? प्रोपोर्शनल कंट्रोलर का रेस्पॉन्स बहुत ठीक था, क्योंकि प्रोपोर्शनेटली ही सेंडिंग a signal. और उसका प्रॉब्लम क्या है? ऑफसेट. सेकंड फेलो ऑफसेट को कंप्लीटली रिमूव. नो ऑफसेट. What is the problem? Very slow. This fellow? Unusually fast. अभी ये फास्ट है या नहीं चेक करना है. कैसा? How to check? Let E equal to sin omega t d by dt of sin omega t cos omega t sin of omega t plus pi by 2. So you see, for sinusoidal input, the phase of the controller output is exhibiting phase lead characteristics. Phase lead का मतलब क्या? It's an indication of fast response. Understand? So because this fellow is sending a control signal before the error has occurred, it means he is anticipating error. Error होने से पहले he is sending a control signal का मतलब क्या? He is anticipating error. You understand? And then he is sending a control signal. That is why another name for this fellow is anticipatory controller. Because he sends a control signal in anticipation of error. ये जो anticipatory nature है, this will not work all the time. You understand? It will not work all the time. Suppose बारिश होने वाला है, समझ के अगर हम छाता लेकर निकल गए, बारिश हुआ तो ठीक है, नहीं हुआ तो ये unnecessary weight है ना हाथ में. ऐसा anticipation may work, may not work also. Anticipate करने से the chances are the tank is becoming empty. So this anticipatory nature may create or may induce instability in a system also. You understand? This is the reason why ये जो integral controllers और derivative controllers है, individually you never use. You always combine it. And the most popular combinations are EI, ED and EID combinations. Individually you can't use these controllers.
अभी लिखवाएंगे.
मैं तो एक जोकर बन गया आप लोग. तो फर्स्ट पॉइंट ब्रेक लेंगे. ये 2 पॉइंट्स तो लिखो पहले इसके बारे में. First point, write down. The disadvantage of this controller is it cannot respond to sudden errors. It cannot respond to sudden errors. Second point. It is also known as anticipatory controller. Anticipatory controller, because it sends a control signal. Sends a control signal in anticipation of error. Sends a control signal in anticipation of error. Third, anticipatory nature may result in instability. In the system. You understand? So the next class will be at 10:30 and we will see the composite modes, PI, PD and
बढ़ जाएगा ये सब
So the first composite action that we are taking is a combination of proportional and integral. P plus I mode. Now whenever you combine these control actions, the analytical equation, I can write it as KPE, KI integral of EDT. I can write this way also. I can combine both the equations. I can also write the combination of this as 1 by TI integral of EDT. They are correct as far as theoretical analysis is concerned. It doesn't make any difference. But these are called as crude forms. The correct way to write the analytical expression of any composite action, the correct way is Kp by Ti. This is the correct way to write the analytical equation of any composite action. You can combine directly also. This is also correct. But this is the most appropriate way of representing the analytical expression. So if you apply Laplace transform to this is Kp into 1 plus 1 by Tis into E of s. So the transfer function of a P plus I controller is of the form of Kp into 1 plus 1 by Tis. Output is P of s, input is E of s. What is the function of any controller? The function of any controller in a system is to eliminate error. Eliminating error means it should have the capability to improve the steady state response characteristics of the system, because error will occur only at steady state. There is no error in transient state. Similarly, the function of a controller is also to improve the transient state characteristics. When can we say that a controller can improve the transient state characteristics of the complete system? When this fellow has good speed of response in tackling the errors. So the function of a controller is to improve both the specifications, transient state as well as steady state. The presence of an integral controller, we have seen, has the capacity to eliminate error. So the integral controller is the presence of an integral controller definitely will eliminate error. What is the disadvantage of a proportional controller? That offset which this fellow is keeping in the system, that gets removed by integral action. Because we have seen when you use an integral controller, error is becoming completely zero. So the offset of a proportional controller is eliminated by the integral. Error will become zero. Water level will come back to set point value. But what is the disadvantage of integral? Whether the sluggishness of integral action is eliminated by proportional or not, we have to check. So one thing we are very sure of is that this controller is capable of improving steady state response characteristics. This we are very sure of. But we are not sure whether this controller is capable of improving the transient state. Whether it can improve the speed of response of a complete system or not, we are not sure. Why? Because we have to check whether the sluggishness of integral is eliminated by proportional or not. How to check that? How to check whether any particular controller has good speed of response or not? How to check? Sinusoidal analysis. So, effect on transient state. Effect on the transient state. We can check by performing sinusoidal analysis. Let E equal to sin omega t. P is equal to Kp sin omega t, Kp by Ti, integral of sin omega t dt. This is Kp sin omega t. This becomes minus Kp by omega Ti cos omega t. The overall controller output will become under root of Kp square plus Kp by omega Ti whole square into sin of omega t plus tan inverse of d by a. Kp will get cancelled, plus of minus will become minus 1 by tan inverse 1 by omega ti. So if you observe, for sinusoidal input, phase of the controller output is exhibiting phase lead characteristics or phase lag characteristics. इसका मतलब क्या? ये जो इंटीग्रल कंट्रोलर का जो sluggishness है, it will remain. इसका मतलब this controller is still slow. Therefore, we say that this controller is capable of improving only steady state characteristics. We can use this controller for eliminating the error only. You understand? ये controller slow है. अगर if you use this controller with any plant, overall system का response भी क्या होगा? Slow ही हो जाएगा. You understand? Now the question is, if this is capable of improving only error, capable of improving only steady state characteristics, eliminating error, then what is the difference between this PI controller and I controller? I controller also is doing the same thing. वो slow है और वो सिर्फ error को ही eliminate कर रहा है. Yes or no? The difference is, in an I controller, the phase lag is 90 degrees. By changing the value of PI, phase lag will not change. और यहाँ पे you can reset the value of PI. By resetting the value of PI, अगर बहुत ही slow है उसका response, some improvement you can make. Response तो slow ही रहेगा, पर कुछ improvement तो कर सकते हैं यहाँ पे. By changing what? वहाँ पे PI को change करो, कुछ भी change करो. Phase lag is how much? ये difference है. Tuning of controllers is possible only in the composite actions. Tuning का मतलब क्या? Proper settings of Kp, Ti and Td. This tuning is possible only in composite actions. Individual I and D we don't use, but this is the reason. You understand? So you can reset the rate of change of control action of integral mode by changing the value of T. That is why this Ti we call it as reset time. And when you use an integral controller with a proportional controller, this combination we also call it as proportional plus reset controller. So क्या कह सकते हैं? Proportional plus, क्योंकि यहाँ पे you can reset the rate of change of controller, but only individual controller you cannot call it as reset controller. It's called as integral controller only. क्योंकि वहाँ पे even if you change PI, it serves no purpose there. समझ में आया? For sinusoidal input, phase of the controller output is exhibiting phase lag characteristics here, which means this controller is similar to phase lag compensator. This controller and phase lag compensator both are similar to each other. What is this phase lag compensator? This is the implementation of a P plus I controller, which is implemented as a phase lag compensator now. This is the implementation. This is V out. This is 1 by Cs, R2, R1, E. This is V1. So V minus V1 by R1 V1 minus V out by R2 CS plus 1 by CS. Since V1 is 0, we have VE into R2 CS plus 1 divided by R1 CS is equal to minus V out. So minus V out will become VE into R2 CS by R1 CS VE by R1 CS. C gets cancelled. Minus V out is equal to R2 by R1 into VE plus this I am writing it as R2 by R1 into 1 by R2C. Multiplying and dividing with R2. 1 by S is integration VE dt. VE by S क्या है? VE by S is nothing but integral of VE dt. Now compare this expression with the standard form. What is Kp value? Kp value is R2 by R1. What is reset time? R2C. What was the time constant of lag compensator we defined? R2. Therefore, the P plus I controller is similar to phase lag compensator. यहाँ पे लेफ्ट हैंड साइड में प्लस P है और यहाँ पे लेफ्ट हैंड साइड में माइनस V आउट है. इसको प्लस बनाने के लिए क्या करना? हाँ, एक इन्वर्टर यूज करना है. यहाँ पे प्लस बनाने के लिए क्या करना है? यहाँ पे you have to use one inverter. And what will be the output of an inverter? Plus P out. Now this becomes the implementation of P plus I controller. समझ में आया? First point, it is capable of improving the steady state response characteristics the steady state response characteristics of the system only. It is capable of improving the steady state response characteristics of the system only. Second point. The integral controller eliminates the offset of proportional controller. The integral controller eliminates the offset of proportional controller. Third, it is also known as proportional plus reset controller. Proportional plus reset controller. Because the rate of change of controller output can be reset by changing the value of reset time Ti. By changing the value of reset time Ti. Next, third point. Fourth point. The sinusoidal input. The phase of the controller output lags by sinusoidal input. The phase of the controller output lags by tan inverse 1 by omega Ti. Lags by tan inverse 1 by omega Ti. Hence, it is similar to phase lag compensator. Next point. In terms of filtering property, it acts as low pass filter. Now this I will explain to you in the next topic, frequency response methods. Why we say that it acts as a low pass. Next, the P plus I controller. Increases the type and order of the system by 1. Increases the type and order of the system by 1. You see, you have one S term in the denominator. इसका transformation is simplified is KP TIS plus KP by TIS. When you use this controller, type 0 will become type 1. Type 1 will become type 2. Order 1 will become order 2. So it increases the type and order by 1. Next, effect on performance specifications. Next subheading, effect on performance specifications. Effect on performance specifications. You see, this effect on performance specifications, whatever we are writing, this is applicable even for phase lag also. This is applicable even for phase lag also. And this is also applicable for only I also. It is also applicable for only I. Exam में पूछा, what is the effect of integral control on peak overshoot? हाँ? ये सर बुझा लेते हैं नहीं, सर ने नहीं पढ़ा है, यही है। ये जो तुम लिख रहे हैं, effect on performance specifications, it is not only applicable for phase lag, it is not only applicable for PI, it is also applicable for only I also. You understand? सुनो इधर. This controller is capable of eliminating error, and the response of this controller to errors is slow. So when you use this controller with any plant, overall response of the system also will become slow. The speed of response of any control system is always defined in terms of rise time, not settling time. It is always defined in terms of rise time. So what is the effect of this controller on rise time of the system? So when you use this controller with any plant, rise time of the system will increase or rise time of the system will reduce. Huh? Rise time पे क्या असर है? Rise time increase होगा या reduce होगा? Rise time will increase. The response is becoming slow. Right. First point. It increases rise time. It increases rise time. You see, rise time and bandwidth are related to each other. Rise time and bandwidth are inversely related to each other. How they are related, we will see in the frequency domain specifications in the next topic. So, as rise time increases, bandwidth will reduce. So, what is the effect of this controller on bandwidth? It reduces the bandwidth. Second point. It reduces bandwidth. It reduces bandwidth. You understand? Now, adding a phase lag compensator is adding a pole or adding a zero? Huh? Pole. Adding a P plus I controller is also adding a pole, because if you look at the transfer function of a PI controller, KP TIS plus KP by TIS. तो पहले origin पे pole है, उसके बाद लेफ्ट साइड में क्या है? Zero है. तो dominant effect, dominant element क्या है यहाँ पे भी? When you add a pole to a system, what is the effect on stability? Huh? It decreases the stability of the system. क्योंकि ये response को slow कर देगा. Response of the system is becoming slow. You understand? Right. Third point. It reduces the stability of the system. It reduces the stability of the system. It reduces the stability of a system. You understand? Now you see, for underdamped systems only you will have peak overshoot. is the peak overshoot. ये राइस टाइम है, इधर सुनो इधर, ये राइस टाइम है, ये पीक ओवरशूट है। ये कंट्रोलर राइस टाइम को क्या कर रहा है? हाँ? जब राइस टाइम बढ़ेगा तो ये पीक ओवरशूट क्या हो रहा है? What is the effect of this control on peak overshoot? Decreases. Peak overshoot decrease हो रहा है, इसका मतलब जीटा क्या हो रहा? Increases damping ratio and hence reduces peak overshoots. Next. Monday तक same time 7:30 to 12. Next. What did you write? It increases the it increases damping ratio and hence reduces peak overshoot. It increases damping ratio and hence reduces peak overshoot. You understand? So this effect on performance specifications, whatever you have written, it is applicable for only I. It is also applicable for phase lag. You understand? Next. P plus D controller. P plus D mode. So the analytical equation is, as I said, you can write KD dE by dt. This is also correct. When you do theoretical analysis, it doesn't make any difference. You can also write here directly TD also. But these are crude forms. The correct way to write the analytical expression of any composite action is, it is Kp TD dE by dt. So this is Kp into 1 plus TdS into E of S. This is the transfer function representation of the P plus D controller. 1 plus TdS, E of S and E of S. You see, with the proportional controller, offset will remain. Anticipatory nature of derivative action also may result in some error. इसका मतलब when you use this controller with a plant, minimum offset error definitely will remain. Minimum of offset error definitely will remain. Which means, is this controller capable of eliminating error? It will keep some error. Minimum of offset error definitely it will keep. That is, minimum error it will keep. So can we say that this controller is capable of improving the steady state response of the system? No, because error it cannot remove. On the contrary, it is keeping some error in the system. So we say that this controller is capable of improving only transient state, speed of response, provided whatever error it is keeping in the system, that should be acceptable in that application. Then only you can use this controller. Definitely some error, definitely it is going to keep. So when you use a PD controller with any plant, you have to observe its effect only on the improvement of speed of response. And whatever error it is going to keep in the system, that error should be acceptable in that application. Then only you can use this PD controller. Otherwise you can't use. So generally, in systems where there are large time constants, like boilers, where time constants are very large, or transportation lag is very large, dead time effects are very large. In such cases, we use these controllers only to improve what? Speed of response. You understand? So effect on transient state can be observed by subjecting the system to sinusoidal input. So let E equal to sin omega t. It is Kp sin omega t, Kp Td d by dt of sin omega t. It is Kp sin omega t, omega Kp Td cos omega t, under root of Kp square omega Kp Td whole square into sin of tan inverse of omega t. So if you observe, for sinusoidal input, the phase of the controller output is leading or lagging. By how much angle it is leading? Tan inverse omega t. Now the difference between only D and PD is, in only D, the phase lead is 90 degrees. You can't change, which means the anticipatory nature of a derivative controller you cannot control there. But here, the anticipatory nature of derivative controller you can control by changing the value of, अगर response बहुत ही fast है, then you can control that response by changing the value of. The advantage is tuning of controller is possible only in opposite actions. So by appropriately tuning the values of Kp, Ti and Td, you can get optimum responses from these controllers. That is possible here, but for individual I and T it is not possible. For sinusoidal input, because the phase of the controller output is exhibiting phase lead characteristic, this controller is similar to phase lead compensator. This is the implementation of a phase lead compensator, which we are now calling it as a P plus D controller. This is the P plus D controller and this is the inverter. This is plus V out, R, V out. This is V1, R1, 1 by C1S. So we have V minus V1 by R1 by R1 CS plus 1 is equal to V1 minus V out by R. So minus V out will become V into R1 CS plus 1 into R2 by R. This will become R2 by R1 into VE plus R2 by R1 into R1C SVE. Output of an inverter is plus V out. It is R2 by R1 into VE plus R2 by R1 into R1C SVE is nothing but dVE by dt. So you observe Kp value is R2 by R1, Ti value is R1C. What was the time constant of phase lag compensator V1? R1C. So we say that this controller is similar to phase lag, phase lead compensator. Now, conventional question number 3 of chapter 3. This was the control loop given. This was the controller Kp plus KDS, and this is the plant K by S into 1 plus Ts. This is C of S and R of S. Now, first one, without P plus D controller. Without P plus D controller, the open loop transfer function is K by S into 1 plus Ts. This is what type and what order? Type 1 and order 2. Now with P plus D controller, the open loop transfer function is K into Kp plus Kds by S into 1 plus Ts. What is the type and order? Type 1 and. So this controller has no effect on type and order of the system. With P controller, the open loop transfer function will be Kp by S into 1 plus Ts. The characteristic equation will become 1 plus Kp by S into 1 plus Ts equal to 0. Ts square S plus Kkp. So S square plus 1 by Ts plus Kkp by T. Omega n value was under root of Kkp by T. And what is zeta value? 2 zeta under root of Kkp by T is 1 by T. Zeta is 1 by 2 root of Kkp T. These are the expressions of zeta and omega n without the derivative controller. Now, we are adding derivative controller. That means it has now become P plus D controller. So the open loop transfer function will become K into Kp plus Kds. Derivative controller we have added here. S into 1 plus Ts. The characteristic equation will become K into Kp plus Kds by S into 1 plus Ts equal to 0. So Ts square S into 1 plus Kkd plus Kkp. S square 1 plus Kkd by T Kkp by T. What is omega n value? Under root of Kkp by T. This is omega n with derivative controller added. 2 zeta under root of Kkp by T is 1 plus Kkd by T, which implies zeta value will be 1 plus Kkd by 2 root of Kkp T. This is zeta with derivative controller added. Fourth one, ESS for unit ramp input. What is ESS? Limit S tends to 0, S1 by S square by 1 plus Kp plus Kds by S into 1 plus Ts. Square S gets cancelled. 1 by Kkp. So you see, minimum of offset error definitely will remain if you use this control. यहाँ तक लिखो, एनालिसिस बाद में करेंगे.
कौन सा क्वेश्चन है? क्वेश्चन 2 बनाया. क्वेश्चन 2 है क्वेश्चन 3? क्वेश्चन 1 है. क्वेश्चन 4 है. क्वेश्चन 4 है. अच्छा है.
It is capable of improving the transient state characteristics of the system only. It is capable of improving the transient state characteristics of the system only. That is speed of response of the system. Is speed of response of the system. Second point. For sinusoidal input, the phase of the controller output leads by tan inverse omega TD. Leads by tan inverse omega TD. Hence, it is similar to phase lead compensator. Hence, it is similar to phase lead compensator. Third point. In terms of filtering property, it acts as high pass filter. It acts as high pass filter. Next, the P plus D controller does not affect the type and order of the system. Does not affect the type and order of the system. Next, effect on performance specifications. Next subhead. Effect on performance specifications. Effect on performance specifications. So you see, this controller is capable of improving the transient state of the system. This controller is capable of improving the speed of response of the system. Speed of response of the system is defined in terms of rise time. So what is the effect of this controller on rise time of the system? Rise time will reduce. So the response is becoming faster. Rise time reduces. So whatever specifications you are writing are applicable for only D as well as phase lead. They are applicable for only D as well as phase lead. Separately, there is the A and first one. It reduces rise time. Second, it increases bandwidth. So bandwidth is increasing. Bandwidth is increasing means noise is getting amplified. Yes or no? Bandwidth is increasing. इसका मतलब क्या? 91.1 when you tune, you listen to songs. 91.11, 12. Increase the bandwidth. What will happen? Signal gets diluted. What is getting amplified? Noise. After a certain value, only noise you will listen. So when bandwidth increases, noise gets amplified. And when noise is getting amplified, S by N ratio, signal to noise ratio, reduces. So what is the effect of this controller on signal to noise ratio? It reduces. You understand? Next, third point. It amplifies noise. And hence reduces S by N ratio. It amplifies noise and hence reduces S by N ratio. Now, adding a phase lead compensator is adding a pole or adding a zero. If you look at this PD controller, transfer function of this PD controller, if you see, ये क्या है? Zero है, pole है. If you look at that system, when you add a PD controller, what are you adding in the transfer function? Zero. When you add zeros to a system, what happens to stability? It increases the stability of the system. It increases the stability of the system. Now listen here. What is the effect of this controller on rise time of the system? Rise time is reducing. Yes or no? Because it is improving the speed of response, it has to reduce the rise time. Only in underdamped response you will find peak overshoots. Only in underdamped response you will find peak overshoot. This is the peak overshoot, this is the rise time. As this rise time reduces, what should happen to peak overshoot? It should increase. Yes or no? But listen. This is the value of theta without derivative controller. This is the value of theta when you have added a derivative controller. What happened to theta? How many times it increased? 1 plus AKD times theta got increased. So in a P plus D controller, when you add a derivative controller, no doubt the rise time will reduce, no doubt. But at the same time, the peak overshoot also will reduce because the derivative controller is increasing the value of theta. Rise time to reduce hoga, but at the same time, the peak overshoot also will get reduced. Right, next. Next point. It reduces peak overshoot. It reduces peak overshoot. It reduces peak overshoot because it increases. The damping ratio zeta. It increases the damping ratio zeta. You understand? Chapter 3 recover. Fourteenth question you see now, 62 page number. How does cascading an integral controller in the forward path affect the relative stability and steady state error? So what is the effect of integral controller on stability? Reduces. What is the effect of integral controller on steady state error? Steady state error, what will happen? Both are reduced. Both are reduced. क्या है answer? D. Which one of the following is an advantage of a PD controller in terms of zeta and omega n? See here. Without derivative controller, this is omega n. With derivative controller, omega n is remaining same. Omega n will remain fixed. Without derivative controller, this is zeta. By adding derivative controller, omega n will remain fixed, zeta will increase. Next, 16th question. A PD controller is used to compensate a system. compared to the uncompensated system, the compensated system will have higher type number. क्या correct है? क्योंकि इसका कोई effect ही नहीं type and order. Reduced damping. No, damping increases. How many times it is increasing? 1 plus. You see, the derivative term only is increasing the damping. Larger transient overshoot. Overshoot will increase. क्या है आंसर? Higher noise. Why higher noise amplification? Because it is increasing bandwidth. Bandwidth increases means noise will get amplified. 18th question. A system is said to possess derivative output compensation. Derivative output compensation का मतलब controller is placed in the feedback path. अब ये conventional question number 1 देखो, ये AS is nothing but derivative controller भी मान सकते हैं ना हम? Yes or no? इसको हमने tachometer feedback example लिया, इसको हम derivative controller भी ले सकते हैं ना? इसका ओमेगा n सेम था. Yes or no? जीटा 0.5 से 0.8 हुआ. You remember? अभी ये this can be considered as derivative controller. AS can be considered as derivative controller, which is placed in the feedback path. तो ये output compensation ही हुआ, correct? अब ये derivative controller का input क्या है? Derivative controller का input क्या है? C of S है. तो a system is said to possess derivative output compensation when the generation of its output depends on what? Rate of change of output. अगर forward path में है तो rate of change of error. You understand? क्या है आंसर? C. Next, page number 77. Page number 77. Look at question number 9. Question number 9. क्या है आंसर? A is the answer. Question number 8. With regard to filtering property, the lead and lag compensators are lead is PD high pass, lag is PI low pass, high pass and low pass. You understand? Next, P plus I plus D mode. It is capable of improving. It is capable of improving both transient and steady state response characteristics of the system. It is capable of improving both transient and steady state response characteristics of the system. Second point. It is similar to lag lead compensator. It is similar to lag lead compensator. Third, in terms of filtering property, in terms of filtering property, it acts as band reject filter. In terms of filtering property, it acts as band reject filter. Next, it increases the type and order of the system by 1. It increases the type and order of the system by 1. Next, effect on performance specifications. Effect on performance specifications. You see, PI controller, only advantage is what? Steady state error it will eliminate. Apart from that, कोई advantage नहीं है. Bandwidth is reducing, rise time is increasing, stability is reducing. ये सारे disadvantages थी. P plus D controller advantages क्या है? Rise time reduce हो रहा, bandwidth increase हो रहा, stability भी increase हो रहा. Yes or no? जो भी advantages है PD के और जो भी advantage है PI का. PI का क्या advantage है? सिर्फ offset का error it is completely steady state error it is removed. These two advantages of PD, advantages of PI are nothing but PID. Right, first one. It reduces rise time. It reduces rise time. Second, it increases bandwidth. Third, it amplifies noise and reduces S by N ratio. It amplifies noise and reduces S by N ratio. Next, it increases stability of the system. It increases stability of the system. Next, it increases damping ratio zeta. It increases damping ratio zeta and hence reduces peak overshoot. And hence reduces peak overshoot. And last one is it eliminates steady state error. It eliminates steady state error between input and output. It eliminates steady state error between input and output. So all the advantages of PD and the advantage of PI you will find in a PID controller. The analytical equation of a PID controller is KPE KP by TI integral of dt KP dd TE by dt. This will become Kp into 1 plus 1 by TIS plus TDS into E of S. It is Kp into 1 plus 1 by TIS plus TDS. E of S is input. P of S is output. So this is implemented as a lag lead compensator. So this is the implementation of a PID controller. we have V minus V1 by R1 C1S plus 1, V1 minus V out by R2 C2S plus 1 by C2S. V into R1 C1S plus 1, R2 C2S plus 1 by R1 C2S. So minus V out is equal to R1 C1 R2 C2S square by R1 C2S V S into R1 C1 plus R2 C2 by R1 C2S V by R1 C2S. Multiply and open the brackets, and every term will get multiplied with V by R1 C2S. S gets cancelled, S square C2 C2 R1 gets cancelled. Minus V out is equal to V into R1 C1 by R1 C2 R2 C2 by R1 C2 plus V by R1 C2S R2 C1 SV. Here R1 C2 C2 gets cancelled. You see, when compared to this R2 by R1 gain, C1 by C2 value will be very small. R2 by R1 multiples of hundreds या thousands में होगा. C1 by C2 मिली माइक्रोफैरेड्स में रहेगा. Suppose अगर ये R2 by R1 100 है, 100 assume, और ये C1 by C2 0.1 है, तो क्या है अभी? ये 100 है, ये 0.1 है, तो इसको कैसा लिख सकते हैं? हाँ? इसका मतलब ये जो C1 by C2 plus R2 by R1, this entire thing I am writing in terms of only R2 by R1. So this equation will become output of an inverter is plus V out, R2 by R1 into V, this is R2 by R1 into 1 by R2 C2 integral of V, R2 by R1 into R1 C1 dV by dt. So if you compare, Kp value will be R2 by R1, Ti value will be R2 C2, Td value will be R1 C2. This becomes the implementation of a PID controller. page number 78. So page number 78, if you see, a three-term controller is described by the equation. ये क्या controller है ये? PID controller. So this controller is used along with the plant. The plant transfer function is given. So when you are applying Laplace transform to write the transfer functions, transfer function is written in terms of input and output by assuming all initial conditions to be 0. So when you are writing when you are applying Laplace transform, integral limits and all, if they are given, you should not consider 1 by ti integral of e of t dt d e of t by dt. This is the three-term controller equation given. So Laplace transform of this will become 20 into 1 plus 1 by EIS plus TDS into E of S. You should not consider these integral limits and all that, because all initial conditions we assume to be 0. So this controller is used along with the plant. This is the controller, and this controller is 20 into EIS plus TDS. This is used along with the plant. The transfer function of this plant or process is given as 40 by 10s square 8es 800. This is the control loop. This is the loop. This is the process or plant. Now if you look at first part of the question, if integral action is not employed, find the derivative time required to make the closed loop damping ratio unity. Integral action is not employed means the open loop transfer function will be of the form of into 1 plus TDS into 4 divided by s square plus 8s plus 8. So you are not employing this integral action. This reduces to PD controller. So construct the characteristic equation 80 into 1 plus TDS by s square plus 8s plus 80 equal to 0. S square plus 8 into 8 plus 80 TD plus 160 equal to 0. Omega n value is root 160, 12.64. 2 zeta into 12.64 is 8 plus. To make the closed loop damping ratio unity means zeta value is given as 1. 2 into 1 is 8 plus 80 t. From this you calculate TD. This comes out to be 0.2 seconds. So this is the derivative time required to make the closed loop damping ratio unity 1. Now if you look at second part of the question, with this value of derivative time maintained, which means you have to put the value of PD here as 0.2. What is the minimum value of reset time that can be used without instability arising? Minimum value of reset time without instability arising means Ti marginal. Yes, a K marginal हमने calculate किया. Above or below K marginal value, system may become unstable. वैसा Ti marginal you have to find, and you have to put in place of Td 0.2, whatever value you calculate. So the open loop transfer function will become 20 TIS plus 20. 20 into 0.2 is 4 TIS square into 4 divided by TIS into, हो गया, now you construct the characteristic equation 80 TIS plus 80, 16 TIS square by S square plus 8S plus 80 equal to 0. TIS cube 80 TIS 16 TIS square plus 80. (24 TIS square) 160 TIS plus 80. S cube 24 S square 160S 80 by Ti equal to 0. So external coefficients, internal coefficients को equate करना to find Ti marginal. So the minimum value of Ti is 0.02 seconds without instability arising.
काहे रख रहा है? अभी और है? हो गया? नहीं है। उसको बोल के क्या है कि नीचे से बच्चा लोग को ऊपर भेज रहे हैं, तो अभी थोड़ा देर बाद छोड़ने के लिए।
Understand? इसके बाद कुछ क्लास है आपका, क्या करोगे घर जाके? ये झूठ नहीं बोलना, स्टडी। एक लास्ट टॉपिक है, वो कर लेंगे, कर लिए तो ये पार्ट 3 आज खत्म हो जाता, कल पार्ट 4 शुरू कर सकते।
क्या बोले सर? क्या लिख रहा था?
In order to compensate for errors when there is any disturbances occurring in the system, we have seen disturbances in a system is shown as This is the representation of the control system with disturbances. These are the disturbances. So one way to eliminate the effect of disturbances is to use controllers here. We have seen just now. PI, PD, PID controllers are used to eliminate the effects of disturbances. That is to eliminate this error which is occurring due to disturbance. There is another scheme to completely eliminate the effect of disturbances in a system. Is feed-forward compensation. In feed-forward compensation, we place one more controller called as feed-forward controller in the feed-forward path like this. This scheme is called as feed-forward compensation scheme. एक कंट्रोलर को ऐसा फीड फॉरवर्ड पाथ में, that means already एक कंट्रोलर है यहाँ पे. You are using one more controller and placing it in this feed forward path. When you place a controller in this path, the effect of disturbances will not be felt in the system at all. You see now, suppose if I want to write C by R, you have to put D of S equal to 0. What is the transfer function? 1 plus G1 of S, G2 of S, H of S. If you want to write C by D, you have to put R of S equal to 0. एक फॉरवर्ड पाथ है G2 और दूसरा फॉरवर्ड पाथ क्या है? GFF, G1, G2. कितने फॉरवर्ड पाथ हो गए? 2. The first forward path is G2, GFF, G1, G2. Denominator will remain same. G2 into H of S. Now if you observe, output of the system is depending and getting affected with respect to both R of S as well as with respect to D of S. G1, G2 divided by 1 plus G1 of S, G2 of S, H of S. So the output of the system is depending on R of S as well as it is getting affected due to D of S. Now to eliminate the effects of disturbances, the effect of disturbances, the condition for feed forward controller GFF is, this should be minus 1 by C. ये condition है. Put GFF as minus 1 by G1. क्या हो गया यहाँ पे? G2 minus G2 कितना हुआ? इसका मतलब effect of disturbance system में दिखेगा ही नहीं. अगर disturbance हुआ system में, तो actually plant में दिखेगा ही नहीं, क्योंकि वो controller is eliminating its effect. This scheme we call it as feed forward compensation. पेज नंबर 60 निकालो. क्वेश्चन नंबर 6. पहले ये देखो, इसके बाद देखो, ये कहीं नहीं आता ना, क्वेश्चन नंबर 6 निकालो और देखो 6th क्वेश्चन को पेज नंबर 60 पे। Now if you look at this block diagram, ये G1 of S क्या है? K into S plus A into S plus C divided by S plus B into S plus D। ये पूरा G1 है। G2 क्या है? G2 of S 1 है। So to eliminate the effect of noise, the condition of feed forward controller GC क्या है कंडीशन? -1 by G1 है। इधर देखो, इधर अगर ये प्लस साइन है यहाँ पे तो ये -1 by G1 होगा। अगर यहाँ पे माइनस साइन है तो ये क्या है? यहाँ पे क्या साइन है? माइनस का मतलब 1 by G1 इसका आंसर। S plus B into S plus B by K into S plus A into S plus C. This is the answer for this problem.
जीवन का इन्वर्सन होता है गीता के साथ में इस दुनिया को कंट्रोल करते हैं। जीवन को गीता करेंगे।
समझ में आया?
भगवान से मिले।
So we have completed 3 parts. 4th part tomorrow will start. 6:30 आ सकते हैं सुबह में?
यस सर।
Sure?
यस सर।
कल 6:30 से क्लास।
सही में 6:30 से है क्या भाई?